In this video now, we will try to use a Smith chart to calculate the input impedance of the T-pi network. Now what do you mean by T-pi network? The circuit is connected in the T form as well as the pi form to which the load is connected. So one such example is given over here. You have a load impedance ZL which is given. All these values first of all are normalized and they are normalized impedances. Okay, so the load is there and it is connected to a section of T-pi network. So you have a pi network and then you have a T-pi network. And using a Smith chart, you are supposed to find out what is ZL. Because how to calculate the input impedance mathematically, you will apply a series parallel connections and start from the load point to the source point and eventually you find out the value of ZL. But that is definitely quite tedious one. So you will have a Smith chart procedure which will make it more faster to calculate the value of ZL. Here you be using completely a Z Smith chart. The same procedure can be done using a ZY Smith chart. But what are the differences in the end? I will just explain. I will be explaining the procedure completely using a Z Smith chart. Okay. So the first step always in this case is to locate the impedance. Okay. So ZL is located. So I am going to locate ZL over here. I have located my impedance ZL. Okay. Now what is the next impedance or what is the next element which is coming to be added to that is Z1. How Z1 is connected? It is connected in parallel. So naturally I am operating on a Z domain. I cannot add element in parallel directly. So I need to go to the Y domain of this Smith chart. Remember this switching of Z to Y and Y to Z, vice versa back forth will continuously happen depending upon how the elements are connected in the network. So considering this particular network which is there, I need to add a Z1 in parallel. Remember Z1 is the impedance which is given, ZL is also impedance which is given. So what I will do for that particular ZL, for that particular value of ZL, I will find out, I will draw the constant gamma circle. Okay, I hope everyone knows how to draw the constant gamma circle. And after drawing the constant gamma circle, take a diametrically opposite point over here. So you are now on the admittance domain. You are using Z Smith chart as a Y Smith chart. So next step, what you should do? Calculate Y1 for that respective Z1. Calculate Y1 for that respective Z1. How you do that? 1 upon Z1. That will give you the value of respective Y1 for that impedance. After that, what you should do? Identify the corresponding R circle, or I should say the corresponding G circle onto which this YL is residing, because now you are on Y domain. So you identify corresponding G circle or R circle on which this YL is residing, and to that particular admittance which is 1 minus JB now, 1 minus JB in nature, to that 1 minus JB in nature admittance, you add the susceptance of Z1, that is 1 upon Z1. Okay, naturally it is negative impedance, rather value is there, so susceptance will be positive. So accordingly calculate that value. Whatever 1 minus JB you are getting over here as the admittance, to that JB part you add that negative positive susceptance which is of Z1. So eventually you will add Z1 here. Again, these movements on the Smith chart will totally depend upon your actual values of additions and subtraction. I am just showing a graphical representation. So appropriate additions and the subtractions of Y1, Y's and Z's are being considered. So whatever the movements which are being shown on the Smith chart, they may not be exactly pertaining to the values which are present, but I am trying to highlight the concept. Okay, so to this YL, I am going to add this Z1 in series or Z1 in parallel. So Y1 is being added, that is the susceptance. Move along respective constant R circle treated as a constant G circle and move up. This point will be here. So this particular addition is being done for the parallel combination of Z1. Okay, remember procedure I will explain again. You have calculated YL from ZL, then you have calculated Y1 from Z1. YL will be indicated as 1 minus JB over here. To that you have added susceptance of 1 upon Z1, and that's why you have moved along constant G circle, which is basically a constant R circle, and you have arrived at this point. Okay, so this is the admit Y at this particular point. This is the admittance at that particular point. What next impedance is coming? It is Z2, which is in series. Naturally, you cannot work on Y domain. You must go back to the corresponding Z domain. So what you will do? You draw a constant gamma circle and take a diametrically opposite point over here. You take a diametrically opposite point over here. So you are now on Z domain. So you have calculated Z for this. You have calculated Z for this. Read that value. It will be 1 minus jx or 1 plus jx depending upon your actual values of the impedances. Okay, the corresponding graph representations I have shown, so that shows the appropriate proportion of addition of respective impedance or susceptance. Fine. So I have come over here. Now after that, locate corresponding R circle, because you are always going to move on corresponding R or corresponding G, which are circles which are there of R equivalent, right? So you identify corresponding R circle over there, and to that you add impedance Z2, which is 1.2J. Okay, there is no one inversion required. Why? Because it is the impedance only and you are working on impedance domain. So you now add to that particular imaginary value, you add Z2 and you move along constant R circle to a new point. So you have added Z2. Okay, now where you are? We are at this point and you are knowing Z. You are knowing Z. What is the next element to be added? Element Z3 in parallel. Naturally, I will be adding now Y3. I will calculate Y3 of 1 by Z3 value. Right? So, but now that element is coming in parallel and I am working on a impedance Smith chart. So, I need to go right from impedance domain to the admittance domain while drawing the respective constant gamma circle and taking a diametrically opposite point. So, the impedance, this Z now is now transformed to the corresponding Y over here. Okay? Is now transformed to the corresponding Y. So now I am going to add element Z3 in series. I am going to add element Z3 in parallel. So you calculate 1 upon Z3 as Y3 and then locate the corresponding R circle for that. After locating the corresponding R circle to that JB part, minus JB part or plus JB part, whatever it is there, to that you add 1 by Z3 susceptance and then move along that respective constant R circle and you will arrive at this point. Okay, so this is the Z3 addition which I have shown in the Smith chart. Fine. So where you are now? You are at this point location now. You are at this point location and this is the admittance at that point. Okay, this is the admittance at that point. What is the next element which is there? What is the next element? You want to add Z4 in series. Naturally, you are on admittance side, so you cannot add directly Z4. So you need to go back to the respective impedance domain. So draw corresponding constant gamma circle and come back to the impedance domain of that. You come back to the impedance domain of that. So here now at this point you are now looking for that corresponding Z. You are now looking for that corresponding Z. So at this point then you can add Z4 value. So after taking a diametrically opposite point, you locate corresponding R circle. So the impedance will be 1 plus or 1 minus Jx. You locate corresponding R circle. So not 1 I should say. Maybe in the earlier discussion also if I mentioned 1, please don't take that as 1. It is basically respective constant R or constant G which is treated as constant R circle. Okay. So here you identify that respective constant R circle. To that you add this Z4. So that addition of the imaginary component will be done. So corresponding equivalent additions will take you to the impedance over here, that is basically your Zn. So that is the value of input impedance and then you multiply that by Z0 to get a denormalized value. Okay, so this is how you will calculate the input impedance of the T-pi network. It is very fast, you can implement it very fast as compared to the mathematical way which you use using series parallel connection, and then that answer does matches very precisely with the value which is obtained using calculations. So So this is how the procedure is done using Z Smith chart. In case of ZY Smith chart, the only difference comes that diametrically switching of the points is not required, because at that particular point for Z you can read corresponding Y, or at that particular point of Y you can read corresponding Z, because all the Jx or Jb charts are present along with respective R and G. So the precise movement should be done appropriately on constant G or constant R circle over there, rather than the switching of diametrically opposite point. That is the only difference if I am going to use the ZY Smith chart for the input impedance calculation, what is needed. Okay, so this is all about the input impedance calculation using ZY Smith chart. Next lecture we will talk about your last topic, that is the compressed Smith chart as well as the frequency response. Thank you.